All right, howdy folks. Welcome to the first day of Unit 11. We are going to be focusing on volume this unit, right? Unit 10 is about area, Unit 11 is about volume. And you might recall that volume is really all about 3D shapes. So I'm talking cubes, I'm talking spheres, I'm talking, pyramids, all that jazz. We will get into it, but before we sort of dive deep into how to find volume of all those shapes, we kind of need the basics of 3D figures, and that's what today is all about. All right, so here's your warm-up. Use the space below. I'm giving you about half a page. Just use the space to draw your best rendition of a cube. That is the warm-up, all right? Go ahead and pause the video now and just draw your cube. All right, I'm back. Here's my cube. How does yours look, right? Do we have something similar maybe? Did you do that thing where you draw the one square and the two square and then you just connect the squares? Yes, no, maybe. All right. So this is, a cube. And one thing that I do just want you to notice is that we've drawn a 3D figure on a 2D space, right? A piece of paper only has 2 dimensions, but we're still drawing this 3D figure. So the actual drawing itself is 2D, but it represents something that's 3D, right? And that just takes a little bit of visualization, yeah, hard word, and just imagination on your part to just see what's happening on the paper and connect that in your mind to a 3D image, right? But there we go, cube. All right, I'm actually going to bring this down here just so I have something to talk about as we summarize things. But we have some terms here for our 3D figures. All right, so first up, a face is a flat surface that forms a boundary of a 3-dimensional solid object. Really what that means is a side of a box or a side of a prism, something like that, right? A face. So I could say that in this cube, I have a face on top, right? That would be my top face. I would have a face on bottom. This would be one of my bases, right? I could have a face on the side, right? This might be a lateral face, right? So basically a face is a side, but we don't like to use the word side because does a side actually mean a side of a face, right? We try to avoid using the word side. So we're talking about a flat surface that has a little bit of area. We're going to use the term face, right? For a cube, you can count this on the cube, or you can sort of think about it like, what if we had, like, if you had dice, right? If you ever played Monopoly or any other board game, dice have 6 possible outcomes, one for each face of the die. So there are 6 faces for a cube, right? 6 faces. All right. An edge is a segment where 2 faces meet. Right, so like I said, we don't like to use the word side because we don't want to confuse that with this segment here. We call this segment an edge, right? And you can see that when I have this top face and this lateral face, those are meeting at this edge, right? So if we are going to count the edges, you can see that you've got 1, 2, 3, 4 edges on the top face. You've got 1, 2, 3, 4 edges on the bottom face, and then we've got 1, 2, 3, 4 lateral edges around the sides. I just said sides again. All right, lateral edges connecting the top face and the bottom face of the cube. So altogether, we've got 3 sets of 4, and that means that there are 12 edges to the cube. All right, and then we've got vertices. All right, so a vertex, plural vertices, but a vertex is a point where 2 or more edges meet. So I could take this edge, and that edge, and those edges are meeting at this point, this vertex, right? So I've got 1, 2, 3, 4 vertices from the top face. I've got 1, 2, 3, 4 vertices from the bottom face, and that about covers all of the faces of our cube. So we've got, I'm sorry, all the vertices. So we've got 8 vertices in a cube. All right. Now, these numbers are really only specific to a cube. Those numbers are going to change depending on what 3-dimensional figure you have. If you have a hexagonal prism, let's say, right, these numbers are going to be different. But hopefully you have an idea of how you can get to these numbers if you just have this drawing, right? Faces, edges, and vertices. All right, let's push ahead now to cross sections. All right, I'm giving you some images here that aren't entirely math-based. One very much looks like it belongs in a biology textbook, right? I guess this one sort of could as well, but it's just sort of, you know, if you were to cut an apple in half. Really, when we talk about cross sections, we're talking about what would happen if you could look directly through across, right, hence cross section, but across the middle of a shape. If you were just to make a clean slice, a little like right through the middle of the shape, what would you see if you looked inside, right? Cross sections. And the reason that we do that is because we want to consider what would happen if we introduce a third dimension onto our shapes, right? So for example, if I take a look at this cross section of our roots here, and I'll just go ahead and just make a little circle-y sort of deal. Let me get this, let me get this nice and lined up here. Come on. So get that nice and lined up, just like that, right? So previously in Unit 10, we would just have a circle and it would just hang out over here on the paper. It'd be just a two-dimensional thing and we could find the angle of that, right? Back in Unit 10. Now what's happening is if we had the circle and we start shifting it upwards, right, off of the paper in the third dimension, so not left or right, not up or down, but sort of off the paper, and I'm kind of trusting that you can see what I'm trying to have you visualize here, right? We sort of get stacks on stacks on stacks of circles, right? So I can duplicate this, and there's another circle, and duplicate it again, and there's another, right? We're going to keep stacking these circles all the way up, and eventually that makes a cylinder, right? If we keep stacking those layers higher and higher and higher. And so it's really all of those areas just kind of added together as layers that give us volume. So that's why we want to know about the cross section so that we can find the area and then layer it up, right? And that'll give us volume. Let's do this again, maybe not with this particular picture, because I feel like it might be getting in the way just a little bit of us trying to visualize and understand what it is that's happening. So let's head into another app here. All right, so here you can see that I've got a cube hanging out in the 3D space. And if I wanted to, I could, hold on, I could just sort of move around, right? Get all sorts of looks at this cube, right? But we've got a cube hanging out in our 3D space, right? Now I'm going to introduce just a few elements here. Oh, not that. That one, right? And you can see that as I'm dragging this plane up and down, right, I'm getting a look at what would happen if I were to slice horizontally across that cube, right? I'm getting to look inside of the cube as to what's happening in the middle, right? Kind of like an elevator, I guess you could say, right? So I'm just scanning up and down, and this is what would happen if I were to slice across the cube, right? But the important thing to note is that this isn't necessarily just for this dimension. So I could turn these off and let's pull in a different point, right? I can get cross sections in another dimension as well. So the previous one was a horizontal dimension, and this one is going to be if I want to make a vertical cut, right? But hopefully you can see that at each individual point along this edge, right, I can get a cross section, and it's when we layer all those cross sections together that we get volume, right? Think of it sort of like a deck of cards, right? So let me actually go back just to drive that point home. If you had a deck of cards and you only had one card, right, it would just sit on the bottom. If you had two cards, it would maybe be that high. If you had three, we'd go a little higher, 4, 5, 6, 7, 8, 9, 10, right, all the way up to 52 cards. But each individual card doesn't fully have, you know, a lot of volume. It mostly has area as a 2D sort of thing. And so when we're stacking all those 2D faces together, that gives us this rectangular prism, and that's how we're getting volume, right? From one dimension, two dimension, and then we have area, and then we start stacking and moving off the plane, off of the page, so to speak. And then we're getting our third dimension. Right, so cubes are nice. Let's do another, just another shape. So I'm gonna hop into this cone. We'll save that. Come on. Oh, there it is. All right, let me get all of this to go away. All right, so now instead of a cube, I have a cone, right? Same sort of deal. You can look at it head on, you can look at it side to side, all around, right? But we have got our cone. Right, I feel like I got, there we go. All right. And then we can do a similar thing. So I am going to introduce, let's see, where is my, there we go. So you can see as well that we can take a horizontal slice across the cone, and that blue ring is really a circle that's showing us what would happen if we were to just slice across and look inside the middle of the cone. All right, so cross section there. I can take that away. And again, we can do that in another dimension as well. So if I were to take a vertical slice across the cone, this is what I might see if I were to open up my cuts, right? Open up those two halves. Cross sections, right? But it's the same thing. So just this cross section on its own has area, but if I take all of those individual little cross sections and start layering them together, I get this 3D shape. All right, so hopefully you're getting a sense of where volume's coming from. You're getting a sense of some of the vocab that we're going to use. We'll dive into a little more vocab in a hot second. And then each of these days of this unit is going to be about getting ways and techniques of finding information about our shapes and then using volume formulas to calculate volume. So very similar to what we did in area, where you had to do a little bit of math and solving to get the pieces that you need, but then at the end you put those into an area formula and calculated the final area. Similar thing, it just this time there's going to be a third dimension, and instead of area, we're going to be looking for volume. All right, but let's go ahead and pop back into the notes. All right. I should mention, by the way, this space was kind of just for you to write some stuff down about cross-section as is needed. Hopefully you did that. If you want to take a moment to pause the video and write something down now, totally fine. All right, otherwise I'm going to trust that we're good to go. So let's come on down here. All right, let's get some summary out. So this is pretty much the summary of where we're going to go with all of our three-dimensional shapes. And it's kind of important that you know what all of these shapes are. All right, so let's go in and let's start labeling some stuff. I'm going to choose a more appropriate color here because I was writing in green, but that doesn't seem appropriate for this set of shapes. All right, so this first one, I'm telling you is a cube, but you wouldn't necessarily know that from the diagram, not unless I told you it was a cube, right? Reason being is because we don't know if all of these shapes are congruent. I'm sorry, all of these edges are congruent, right? If I tell you that all those edges are congruent and that all of the faces are perpendicular, right? All the edges are perpendicular, then you know it's a cube, right? But if we had just, let's say, a square on the bottom, but the height didn't have the same dimensions, this wouldn't be a cube, it would be a rectangular prism. All right, and a prism really just means that we've got a base, right? So we've got a rectangle on this side, and then that rectangle gets stacked and stacked and stacked and stacked and stacked and stacked and stacked all the way down, and it ends with a congruent base on the other side, right? So our two rectangles here and there, those two rectangles are congruent, right? And every cross section in between is congruent, right? That's how we're defining prism here. So if you have a prism with a rectangular face, we call that a rectangular prism. All right, we can also have other types of prisms. So if I had this triangle, so both of these bases are congruent, and then I take a cross section and it is the same as the bases, it is again a prism, but the base is a triangle, so we call that a triangular prism. right? So really, it is important that I point out that a cube is a type of rectangular prism, sort of the way that a square is a type of rectangle, right? The only difference here is that the rectangular prism doesn't necessarily have uniform dimensions all around. So this length is greater than any of these edges. But in a cube, if I were to get rid of that, and let's say that all of the dimensions had a length of 2, right? This is just a rectangular prism with uniform dimensions. Right, we've got one more type of prism in this box, but it won't necessarily be the only type of prism that we see, because we really can make a prism out of any shape, right, as long as it satisfies our rules for prism. But so this could be like a circle, it could be an octagon, it could be a decagon, it could be whatever. But in this particular case, you might notice that this is a, let me try to get this right here, that this is a pentagon, right? And that pentagon congruent on the bottom, that pentagon the same in the cross section, right? So this is what we call a pentagonal prism. You might hear people say pentagonal. I don't really like how that sounds. I say pentagonal, but you can see where that's coming from, right? You've got a pentagon, and then we're just going to make it an adjective, pentagonal. Right, but again, you could do this with a hexagon, octagon, decagon, any type of prism. Right, and then I'm going to just sort of jump into the round shapes really quick, just to make a point since we're talking about prisms. You might know this shape as a cylinder, but it's probably worth pointing out that a cylinder is kind of like a circular prism. Right, we have a circle for a base, and that circle is the same on the other face and is the same in the cross section. So we call it a cylinder, but we're going to treat it the same as a circular prism. All right, let's hop over here. So you can see that we've got a square base, and it meets, right, all these edges at a common vertex. So this is a pyramid. But throughout this unit, you can't just be saying pyramid. You really do need to be specific about what type of pyramid it is. So in this case, we have a square pyramid. Right, we're getting that from what shape the base is. The reason that we need that is because we need to distinguish from our other type of pyramid. Right, we can see that we've got a shape on bottom, looks like a hexagon. And then all these edges are meeting at a common vertex. But again, we need to distinguish between our pyramids. So we're calling this a hexagonal pyramid. Right, and then you're going to recognize this shape as a cone, right? But it's also worth pointing out that just like the cylinder was sort of like a circular prism, this cone has a circle for a base. All of those edges are meeting at a common vertex. So a cone is very much like a circular pyramid, and we will treat those kind of the same. Right, you'll even see on the formula sheet, which is available in Canvas, please download that, print it off, get it marked up, get it ready to go. Because again, you're gonna be able to use it on your assessment. But you're gonna see when you look at that formula sheet, we even give you pretty much the same formula for cones as we do for pyramids. It's just sort of up to you to work through that appropriately. Right, and then our last one. So if you didn't notice the shading and you just looked at it sort of as it is on the page, this would be a circle. But really what we're looking at here is a sphere. So that has one, oh, don't know how that happened, very strange. That sort of has one, oh my goodness. Beans. You've got to be kidding me on this one. Come on, do it one more time. Hey, there it is. Right. So a sphere has what we call a great circle all the way around. So if you were to cut directly down the middle, you would see this circle as its face, right? And that circle just has a radius, but every point on the sphere is the same distance from the center of the sphere. So just imagine this circle just spinning all the way around, right? And that's how we're generating the sphere. One thing that I do want to point out is if you have a sphere and you cut it in half, so think of just like a big giant salad bowl, right? If it's exactly half of a sphere, we call that a hemisphere. So half of a circle was a semicircle, half of a sphere is a hemisphere with an H. Right? But if it's the entire thing, we call that a sphere. All right, so this is sort of your intro into what we're going to be diving into through this unit. Hopefully you've seen some of these things before, but we will be, well, just the shapes, not necessarily calculating things, but we will be diving into how to calculate all these volumes and how to approach all these shapes. Really, this is kind of it for today, so go ahead and upload your notes. Have a great weekend, and I will see you on Monday.